All right, welcome back. Time for the definite integral. So, remember the state of the affairs is we had the Riemann sum R was the sum of the f of cj's delta xj's, j equals 1 to n. Think of the c's as, the f of c's is giving you the height and the delta x is the width, and it approximated sort of the signed area for the graph of f, where if this is A and this is B, and this is the graph of f, you count this area with a plus and this area with a negative. So it's this area minus, the top area minus the bottom area. And that's what the Riemann sum was approximating. And it seemed intuitive that as the delta x's got smaller and smaller, the approximation got better and better, and that in the limit it should be exact. And that limit is the definition of the definite integral. Definite integral. So definition, the definite integral of the function f over the interval a to b is written with this notation. That sign is like a very shallow elongated s, the integral sign, and that's because it's related to the letter s for sum that came about in the sum part of the Riemann sum. So that elongated s looks like an s on purpose. Anyway, it's called the integral of f dx, and by definition you take the limit as all the delta xj's go to 0 of the Riemann sum. So the sum from j equals 1 up to capital N, f of cj delta xj. All right? And the theorem is, since that's a complicated limit and most of the time limits don't exist, if f is continuous, then in fact this thing exists. Okay? In fact, you can get by with a lot less than continuity. If you just have a finite number of discontinuities, it'll still exist. And in fact, you can get by with even less than that. But for us, that's the easiest thing to say. A finite number of discontinuities, you'll still get existence here. All right. Now, it's also a theorem that the integral from a to b of f of x is the exact signed area. Between f and the x-axis. And again, remember, that means you count areas above the graph with a plus and areas below it with a minus. Okay. Now, let's take these two theorems as a fact and use them to figure out what some integrals are right now. Because if we had to use the definition here, it's true we can do it for incredibly simple functions, but that's all that we can use this definition directly on. We need tricks to evaluate this limit. But assuming this area theorem, we can actually calculate the integral in a couple cases really well. So here's the first example. How do you integrate the function 1? Okay. Well, by the area thing, you should go from a to b. You should graph the function, which looks like that. And then you should calculate this area here. So this thing should be the area of this. Well, that's easy. The area of that is just b minus a. So from this, we get the integral from a to b of 1 is actually just b minus a. All right. First integral done. Let's do one a little harder. The integral from a to b of the function x dx. Well, how am I supposed to do that? This is supposed to be an area under a graph, so let's graph it. This is the function y is equal to x. Okay, so it's a 45-degree line, and we're supposed to go from A out to B and calculate that area, and that should be the answer. Well, you can think of that area as the area of that bigger triangle minus that area of the small one. Okay? And since it's a 45-degree line, the height is b here, the height is a, so we get 1/2 b squared minus 1/2 a squared. So, the integral from a to b of x dx is 1/2 b squared minus 1/2 a squared. All right, that's as far as our symbol formulas go, but we'll use this fact for examples, and we'll show why it works later. In fact, you get a similar formula for all of these polynomial things. The integral from a to b of x to the n dx, we did now, so above we did the case where x is equal to 0 and the case where x is equal to 1. And you notice that the first power got bumped up to a second power and the 0th power got bumped up to a 1. So it's not too hard to guess that that the answer is going to be this. And it turns out this is correct. You increase the power n to n plus 1, plug in the a's and b's there, and have to divide out by the n plus 1. As a special case, just so you see it in a special case, the integral of x squared will be 1/3 x cubed minus 1/3, 1/3 b cubed minus 1/3 a cubed. All right, that's it for the definition and a couple examples of the definite integral. Ciao.